Respected faculty, I'm Sushana Islam Mim, and I'm going to present the paper Simple Yet Powerful Simplical Our Neural Network with my teammates. And at first, I'm going to talk about why SaNN. So, SaNN's revolution deep learning for understanding complex structures like simplification complexes. They are far more efficient than traditional methods for like SaNNs, and using pre-aggregated features tailored to these structures, SaNNs outperform existing tests for graph structures while being computationally economical, enabling effective prediction, analysis, and classification of graphs. So moving forward to the next slide, here we can see the related works where the author names and the contribution is given over here. So at first I'm going to talk about Bodnar et al. So Badner and colleagues proposed a novel SaNN that includes innovative techniques for aggregating information from neighborhood simplices and combining features in a meaningful way. So next I'm going to talk about Ebeli et al. He introduced a variation of SaNN model with novel aggregation and transformation function. So these functions likely aim to improve the expression power or efficiency of SaNN compared to traditional approaches. And Roddenberry et al. Basically, he aim to simplify the architecture or computation of SaNNs to improve the efficiency and scalability. Most of the author did the same thing. They improved the scalability and efficiency of the from their paper. So basically, Young et al. Addresses scalability challenges in higher order graph-based neural network and proposed a simplified approach. And then we can see that Cheng et al. And Desai et al. Also did the Doshi and Chenpur did the same thing. So Rossi et al. Then presented scalable inception graph neural networks for improved efficiency in GNNs, and Yu et al. Also introduced simple gulf convolutional network for as an efficient GNN model in their and likely prioritize simplicity and efficiency in their architecture and computation. Thank you so much. Now my next teammate is going to elaborate the next part.
Assalamu alaikum, I am Samsun Harpreeti. I will explain the proposal and methodology. Simplicially, our neural network model is a scalable model with a constant runtime and memory requirements independent of the size of the simplicial complex and the density of interactions in it. Simplicial layer neural network is based on pre-aggregated simplicial layer features as inputs to a neural network. So it has a strong simplicial structural inductive bias. There are two main key components: the pre-computation of simplicial layer features and the learning from these features to obtain task-specific embeddings. The model operates on case simplices, aggregating information from different neighborhoods of and transforming the features using nonlinear functions. There are two figures. The first figure showing pre-computing simplicial layer features, and the second one learning from simplicial layer features. Pre-computing simplicial layer features are collected from the T-hop upper lower boundary and co-boundary neighborhoods of a case simplex. Simplicial layer features are computed iteratively by aggregating information from different neighborhood refs. Neighborhood aggregation functions update features vectors using T-1 hop layer features. The final aggregated T-hop layer embedding of a case simplex is obtained by combining partial updates. Learning from simplicial layer features. Learnable nonlinear transformation functions transform pre-computed features into embeddings suitable for the task. Embedding of case simplices from different hops are combined using a function theta k. The process is repeated for different depths of neighborhood information. Computational complexity. Simplicial layer neural network incurs lower time complexity compared to existing simplicial neural network models. Time complexity of simplicial layer neural network is of 3 nkd to the power 2k plus nkd to the power 2k minus 1 plus nkd to the power 2k plus 1, significantly smaller than existing 3-layer simplicial neural network models. Simplicial layer neural network demonstrate almost constant forward pass runtime for simplicial complexes of any size. There are theoretical characterization and properties of simplicial layer neural network. The characterization is expressive power over Westphaler Lehman test and comparison with MPSN, and the properties, some properties: permutation equivariance, orientation equivariance, and simplicial awareness. Simplicial layer neural network is proven to be permutation equivariant due to the permutation equivariance of the proposed aggregation scheme and the use of MLPS. Simplicial layer neural network is orientation equivariant when all activation functions in all networks are odd. Simplicial, our neural network is designed to be aware of the simplicial structure up to a given order, emphasizing the importance of boundary matrices in its embeddings. That's it.
Result of a recent research on advancing image classification through a novel hybrid approach. In this study, we explored the combination of self-supervised pre-training with supervised fine-tuning to push the boundaries of performance in this critical area of computer vision. Our research yielded some exciting outcomes. Firstly, we are able to achieve remarkable results on several benchmark datasets including CIFAR-10, CIFAR-100 and ImageNet by harnessing the power of self-supervised pre-training to learn rich representation from enabled data, and then fine-tuning the model on task-specific rating the efficiency of our approach across a range of classification tasks. Moreover, our findings underscored the effectiveness of self-supervised pre-training in learning robust representation by leveraging unleveled data. Our model developed a nuanced understanding of underlying structure of image, leading to improved generalization performance of a downstream tasks. These aspects of our research opens up exciting possibilities for application where labeled data may be scarce or noisy. In addition, such as batch size, learning rate, and impact on model performance. Understanding the nuances of these hyperparameters is crucial for fine-tuning models to achieve optimal results in real-world scenarios. Furthermore, our ablation studies allowed us to dissect the components of our hybrid approach and analyze their individual contributions. By systematically removing or modifying certain aspects of the architecture, we gain deeper insights into the underlying mechanism driving the success of our approach. This understanding will guide future research endeavor in further optimizing and refining our methodology. In conclusion, our research represents a significant advancement in the field of image classification. By combining self-supervised pre-training with supervised fine-tuning, we have demonstrated state-of-the-art performance and provided valuable insights into the mechanism of representation learning in deep neural networks. We believe that our findings pave the way for future innovation in computer vision and beyond. Thank you.
Thank you, Mithila. So this is Sakib Rakoni. My ID is 232373004. Now I'll say about the simple neural network. In this section, we have seen the generic models of SaNN, and these models are SaNN, MPSN, SCON, SaNN, and C2CNN. In the second, we will see the comparison of NN. In this, we will see the existing models of SaNN, which is the dominated by the first term increment feature aggregation in every layer, and a proposed model is given which is used for the neighborhood aggregation done before hood, and the efficiency of the comparison is more or better than the SaNN. In the third section, we will see about the SWL test. SWL test. It is an iterative algorithm that assigns color to all the simple in the simply complex. This means this is a method discussed between different shapes based on their properties. The algorithm works by updating their color of the simple through neighborhood features aggregation. This means this takes into an account the color of the simplest. The SWL test is more powerful than the WL test. Now, in the other section, the proof of the theorem. In the proof of the theorem, we will see that the lambda d1, which is given, and we will prove that WL cooling of the node is iteration can be repeated by the following equation. And we have produced this equation. The update of the WL cooling of node of iteration t is given below. Now, Sania Apu will tell about more for the SWL test. Thank you.
Assalamu alaikum. I am Sania Azmi, and thank you, Rokani. I'll be starting from here. It's kind of really with the time constraint to be explaining all of this complex terminologies and everything. It's kind of a little bit a challenge. Anyways, I will be going really fast. So it's an extrapolation of what Rokani has said about the SWL test, and here I'll be talking with the lemmas. Now, it has been applied from model like MPSN, and basically we're talking about its ability to distinguish between non-isomorphic simplicial complexes. Now, just to before, what is simplices? Simplices could be really, they start with, they're basically, they could be graphs, they could be edges, they could be triangles, they could be higher order formations like triangles, they could be vertices like that, you know. These are kind of talking about relationships. Anyways, so the next lemma, basically they talk about that, you know, SWL coloring after each iteration. What it means and what is SWL coloring and what's happening here. Basically, let's say I start with the simplest. I start with three simplest, and as I said, it could be. Let's just say in the real world. Let's say our group members, Saki, Brokuni, and I. Basically, we three of us we are singular simplest of with zero, and then we have a triangular sort of like a connection. Now, what happens is like after one iteration, it could happen like Rokuni and Saki become friend, I and Rokuni become friend, something like that. So very different sort of different connections is formed at different vertices, what you call that, simplices is formed as it goes by, you know, after each iterations into the algorithms. Now, its ability is to be able to distinguish them, and each state we are actually distinguishing them in the using a color, and that's what we call the SWL coloring actually. Okay, in this slide, we will be basically talking about the coloring that happens, and they are actually represented by the equations. You can see that, but there is a thing that is important. We can see at the bottom of the slide is about the injective function. Injective function basically means it makes sure that this is a one-to-one function. I mean, each distinctive input is going to give you each distinctive output. It's simple as that. And basically, let's just say the relationship. So Sakib and Rokuni, me and Sakib has kind of like formed. We have to make sure like these two are different, and so that the model do not really distinguish them. Now you can be thinking how it distinguishes them. Again, as I said, as it goes into higher topological order, there is a possibility because all of these complexes might not be able to distinguish, and this is a problem we will see. It's of this what you call the model, but nevertheless, even if it's the limitations, as we can see, non-injectivity in k-regular simplicial complexes. In some cases, the aggregator function that we are using might not be giving what I have talked about previously. You know, it could give. Let's just say the example that has been explained here: two different complexes. They have the lower two triangular property, and let's just say they're connected to triangular simplices. You know, it just say. But they are just structurally different. There's structurally different relationships, but for some reason they're giving a similar output. And why does it happen? Or more the fact it can actually happen in certain conditions. It happens, but nevertheless we're actually getting a good result still. We can see that in again in the next slides. And according to the paper, it could happen for several reasons, and they have included to say like they could be pre-aggregating features they are using from taking from different neighborhood hops, which are then transformed using nonlinear functions to obtain simplistically aware embeddings. This is something I think our members have already talked about. Its design ensures permutation equivariance, orientation equivariance, and simplicial awareness, allowing it to effectively capture the higher order interactions with simplicial aware complexes. Anyways, in this slide, basically, just is mostly the results we're talking about, and we have seen in the SW test, you could see that actually performed well in distinguishing the non-isomorphic graphs, despite on occasional, problems. I mean, occasionally they were the aggregating function not able to actually distinguish, but nevertheless, it really works. Actually, it really works well, and we talked about this part, higher order topological information, what it is. Basically, the main part of this paper is it's able to do more than Paris function. It could be making a lot of connections, and it could be aggregating those functions. It could be basically taking a summary of all of those things and still be able to perform well. And here, basically, I've talked about the accuracy in trajectory prediction, simplicial closure prediction, graph classification. These things I think I've just written how much they have like performed well as part of the paper, and they will be discussed more in detail by Rabia. Thank you.
Hello, I'm Rabia. I took to 60 watch. Now I am discussing about experimental setup and data sets. First of all, trajectory prediction. This methodology employs deep learning, specifically in the SaNN architecture for trajectory prediction. It involves preprocessing trajectory data, aggregating features, and splitting data for training and testing. SaNN learns is embedding map to node embeddings, predicting successor nodes using a decoder MLP. Training utilizes supervised learning with cause entropy loss and early stopping. The approach prioritizes orientation equivalence and utilizes standard activation function. Then simplical closure prediction. The experiment aims to predict whether open triangles in simplicial complexes will close. Data is split into training, validation, and testing sets. Features are computed for each simplex, and MLP is used to predict triangle closure probability. SaNN is employed for training with binary cross entropy loss and early stopping. Datasets are heavily skewed with more negative examples. Positive examples are oversampled and weights are used in the loss function. Then graph classification. This methodology outlines the process for graph classification using simplicial neural network. It involves converting graphs to simplicial complexes, employing cross-validation for data splitting, and utilizing SaNN with a specific readout function for embedding. The model is trained using supervised learning with a cross-entropy loss function and early stopping. Injectivity preservation is proven in an appendix. Then summation and concatenation. And the uniqueness of representations obtained from different layers or hubs in a graph or neural network model. It introduces functions that map aggregated features of case simplices to unique representations and highlights the concatenation of embeddings from different layers to capture information from various parts of graph. The injectivity of the network is maintained, ensuring unique outputs for distinct inputs. Then ablation study. The excerpt describes ablation experiments conducted on the SaNN model to assess the impact of features from varying depth of neighborhood and different orders of simplices across trajectory classification, simplicial closure prediction, and graph classification tasks. Results show that combining features from different depths enhances performance compared to using features from the specific depth. Local information one hop is crucial, while three hop information is less relevant than with combined features performs using specific depths with SaNN equal to 2 performing better than SaNN equal to 3. This suggests trade-off between performance and runtime, particularly for graph classification. Second one, these experiments on the impact of different orders of simplices on tasks like simplicial closure prediction and graph classification. Results show that combining features from various orders improves performance. In simplicial closure prediction, edges of open triangles are crucial, while for graph classification, higher order is implies yield poor results due to small graph size. Combining embedding of different orders outperforms using only one order, aligning with theoretical expectations. That's all of my presentation. Thank you, everyone.